Okay, we start where we've left off last time with hadronic interactions. We already discussed ionization, Bethe-Bloch formula, the interactions of photons with matter, Bremsstrahlung, all these are very important. Hadronic interactions in the Hadron Collider are certainly the most abundant interactions and the most diverse ones. So the hadrons interact, as we've discussed last time. I repeat quickly, inelastically with single nuclei inside the nucleus. So you have an incoming hadron hitting the nucleus, and then a host of reaction takes place, producing other charged and neutral hadrons. In the first steps of the interaction, it's important how many pi zeros are produced, because the pi zeros will decay to photons, and the photons will trigger an electromagnetic cascade. So the parts of the energy will go into electromagnetic interactions and look similar to incident electrons and photons. Moreover, at the time scale of 10 to the minus 22 seconds, which is instantaneous, essentially for purposes of detector applications, spallation and evaporation can take place, and these can also produce photons. The secondary hadronic decay products then subsequently interact with further nuclei, and because neutral particles can travel a long distance before they actually hit the nucleus. Remember, the time scale of this, the length scale ratios of the atom to the nucleus is 10 to the 5. So there's only, if a particle is not electromagnetically interacting, can travel a significant distance in the detector material, and therefore the shower development is on a longer length scale than the electromagnetic ones. The spread of the energy between the electromagnetic shower component and the hadronic one is a quantity that widely fluctuates. So if you have an incoming hadron setting off this cascade, it can easily produce 90% or so of electromagnetic interaction, only 10% hadronic, and the next equivalent incoming hadron can do the opposite. So these fluctuations in the showers for hadronic signals is very large, and it greatly limits what we can achieve in terms of resolution of jet momentum reconstruction, for example. After all, we start off with a quark. A quark, as we've discussed a few times, hadronizes, produces plenty of particles, and those plenty of incident high energetic hadrons all produce these widely fluctuating showers, and therefore the physics of jet reconstruction is in its nature is a stochastic process with large fluctuations from hadron to hadron and from jet to jet. And therefore, the resolution in the important physics observables that we want to extract is limited. Let's compare hadronic and electromagnetic showers. I've mentioned them, but we did not discuss them in some detail. The hadronic interaction is stronger, we know that, it's a strong interaction, but it has a very short range. An exponential law is a good description, so we make the same ansatz as we do with the EM showers. The length parameter is called the absorption length. Do not confuse it with the interaction length. The interaction length is the length at which a charged particle's energy or momentum drops to 1 over E, according to just from its electromagnetic interactions. The absorption length is the equivalent for the strong interaction. So these two terms should not be confused. We call the absorption length lambda, and the radiation length was x naught. Now, lambda is given by Beer-Lambert's law that we derived earlier. It is proportional to the number of nuclei in the nucleus, and because we've already discussed that the inelastic cross-section roughly scales with a to the power of 2/3, we can take the ratio here and get the a to the 1/3. However, the density also we can assume very roughly to be proportional to a, and hence the absorption length very roughly for different material scales with the power of -2/3. So let's look at the difference of the shower evolution between electromagnetic showers and hadronic showers. The top plot shows a comparison of 100 GeV electron hitting ion and 100 GeV pion hitting ion. Ion is not a material that is instrumented, so this is a pure simulation. However, you see a completely different picture. The energy loss of photons and electrons is driven by for these energies completely by Bremsstrahlung and pair production, and that leads to a foreseeable short shower development, because there is no neutral particle. Traveling a long distance. The photon, as we've seen, will undergo pair production with a very high cross section. The neutral component in the shower, that's not only neutrons, there can be other neutral hadrons as well, leads to the picture shown at the bottom. The hadron shower extends much more deeply into the material, and where violent hadronic interactions take place deep in the shower, there's always a certain electromagnetic component, as we've discussed, electromagnetic component produced, yielding the picture of long tracks of hadronic particles traveling wide distances in the material, and then causing more shower development with electromagnetic components. So the shower depth roughly grows logarithmically with energy. The bottom plot shows lead tungstate. It's unfortunate that I cannot show you the crystal of that I cannot give you in person an example of the CMS calorimetry crystal. It is it looks like glass, but it is lead tungstate, extremely heavy, 5 × 5 centimeter times 50 centimeter, I think 50 centimeter long, very heavy, can almost not hold it in one hand. And that's the material the CMS electromagnetic calorimeter is composed of. You see here the depth in terms of radiation length, and the shower, the energy deposit relative to the depth, and how it grows logarithmically with energy. So that allows us, in fact, to build particle detectors with a calorimeter detector inside other detectors. Imagine this would scale linearly. It would be impossible to detect particles in an energy range from 1 GeV to 1 TeV. That's a factor 1,000, but only a few steps in terms of radiation length. There is a common misunderstanding in where in the calorimeter the energy is deposited. The misunderstanding is the following. You have an incident reaction. Let's think about an electromagnetic interaction. We have an incident reaction, say an electron comes in, and then that electron across one radiation length, so that would be where my mouse cursor is here in the diagram, around one radiation length, the electron's energy drops to a ratio of 1/E. Now, that's certainly true, but that does not mean that it deposited 2/3 of its energy. The reason is that the highly energetic, the 100 GeV electron, undergoes only a few reactions in the beginning. So indeed, it undergoes on average 1 or 2 interactions, hence its momentum drops significantly. That explains why the shortness. I mean, that defines the radiation length. However, those particles are still highly energetic to travel deeper into the detector, where they undergo further and similar interactions, and the cascade develops. The real deposition of the energy happens. Let's go back. Where does it happen? A good example is well, let's take this one. The real I wanted to show you the energy loss of the electrons. Where is it? I think I did not go far enough. Yeah, here it is. So we start off with GeV energies, or 100 GeV. That was the example for the shower. We start off, that's MeV, that's 100 MeV. So we start to the right of this distribution. And then the electron undergoes Bremsstrahlung processes that are proportional to this to c squared of the material, and energy is lost. Now, per radiation length, the energy scale of the shower particle drop roughly by a constant factor. So you go down this slope. Remember, there's a 1/E here, so it's actually if you plot the energy loss versus energy, there is a very steep decline here. So you roll down this curve until you hit the critical energy. The critical energy is the lowest energy loss. And beyond that, the energy loss is you're down in the MeV range, is extremely steep, and the particles quickly thermalize. So if we go back to our shower picture to explain this logarithmic behavior, what happens is that while we're rolling down the energy loss for very highly energetic electrons and photons, it takes a while. And it takes a while until we reach the critical energy, which would be around here, and then the particles really deposit their energy. And because at each interaction, the relative energy loss from one generation of shower particles to the next generation of shower particles is constant, the penetration depth becomes a logarithmic function of the incident energies. So you can imagine that going from 10 GeV to 1 GeV needs a few radiation lengths, and that is the same number as going from 100 GeV to 10 GeV, just because the relative energy loss is roughly proportional to the energy itself. Okay, so that means there is no contradiction between the energy loss of the incident particle, which indeed happens very quickly after the first interactions, and the deposit of the shower energy much deeper in the calorimetry. It also explains why we have to build the detectors many radiation length, and for hadronic interactions, many absorption length deep. Typical numbers are 20, 25 or so. Here are different materials. For building calorimeter detectors, it's actually beneficial to have a similar response of the electromagnetic and the hadronic showers. The reason is that the fluctuations between the electromagnetic and the hadronic shower component should, on average, cancel. The low C materials have a lower ratio of the interaction length to the absorption length, and that's beneficial for building such calorimeters. If that ratio is very large, like for the high C materials, then this is indicative of it. This shows that the EM component is the EM component induces a larger ionization signal than the hadronic energy deposit. So typically we want low C materials for compensating calorimetry, but that is a topic of a future lecture. So now we stop the discussion of the interactions of particles with matter. Are there any questions on this? Maybe I can stop the recording. So your questions will not go on YouTube.